Okay, let's see. How do I get the participants? Okay. Okay, so this is just how do I stack these multiple perceptrons together? Yeah, so I have, let's say, tweets. These are words. Each one would have a word. And then I can combine these, right? These, everyone is a perceptron, and I can combine these perceptron in any logical functions I want, right?
Sir, we should learn the weights before.
Yes, you, of course. That's your job would be to learn the weights from the training set. Only these weights. Then you're combining them in a, let's say, XOR function.
Sir, for the first perceptron, the addition of the 3 weights becomes the weight for the second perceptron?
No, it becomes the input, right? You pass it through the signal. It becomes the input for the second perceptron. The second perceptron, this one, has a weight of 1. Yeah, so 1 minus 1.5, there's no weights here to learn. There are no weights here to
I didn't fully understand. لما في weight بآخر واحدة؟
Because I want to do XOR. I want to have, this is H1, okay? This is H2. So this is an individual perceptron. This is an individual perceptron. I want to combine them now as an XOR. Yeah, so H1, H2 complement plus H2 plus H1 complement H2, right? That's how I do XOR. This whole network, the rest of the network is for XOR. And this is the first perceptron. This is the second perceptron. Got it? It's just an idea, abstract idea, a little bit. Yeah, we'll see how this relates to neural networks. You don't have to worry too much about this. Just an abstract idea about the power of creating layers of perceptrons. Yeah. So this is how neural.
I just didn't understand how the outputs are here. W1 times X, W2 times X. If the output, I don't understand how the weight contributes to the output one.
Basically the following, right? I have W1.x is what? Is basically a vector of 3 weights. W0, W1, W2. Okay? In the blue line.
Yeah, okay.
W2 is 3 weights. W0, W1, W2. Okay? You sum these guys.
Okay.
Times the feature value. Pass it through this hard threshold, the sign. That gives you +1 or -1 here. Okay? So +1 or -1. +1 or -1. You take this, and then you take the +1 or -1 that coming from here. +1, -1. You apply this weight, so minus times -1 times +1 times -1.5. That passes it through the sign. That gives you H1, H2 a complement. Right, the product of H1 and H2 complement, the ANDing of H1 and H2 complement. Yeah, which what we wanted to achieve here. We said H of X is equal to H1, H2 complement. Yeah, so this region or this region.
Okay, so that's how we got the H1, H2 complement of it.
Yes, yes, yes. So this part of the layer, part of the network, is to get the H1, H2 complement and H2, H1 complement. Yeah, so this is for this, and this is for getting H1 and H2 from the features.
Okay, okay, thank you.
Right? You're welcome. This is called the 3 layers feed-forward perceptron. Yeah, so this is how neural networks initially started. Started with this multi-layer perceptron. Nobody refers to it as multi-layer perceptron anymore, and we'll see, right, a more general form of this idea. But the idea is that, you know, layering perceptron together is very powerful, right? Can really approximate any function in the world. So why is it a 3-layer feed-forward perceptron? Feed-forward because it's going from this direction. That's the input, and that's the output. So it's forward. And 3 layers because I have 1 layer, 2 layers, 3 layers. So I have 3 layers of perceptrons in the network. Okay. It's a very powerful model. Assume the target function looked like this. So it's a circle. So I have inside is positive, outside is negative. Using 8 perceptrons, I can combine 8 perceptrons using some logical function. So it basically I can come up with a logical function like what we did with XOR between 2 high perceptrons. I can come up with a logical function that represents this, right? And you see this is almost like a circle, yeah? So basically in this region, right? This, I don't know what type of polygon this is, but in this region, positive, and outside is negative. Yeah. If I use 16 perceptrons, I even get closer to a circle, and so on. The more perceptrons I use, the closer I can get to approximate any target function I have. It can be any number, and the more you have perceptrons, what is the issue? The more parameters you have, right, and the more you need to pay for in terms of generalization. Overfitting, exactly. So the more, right, perceptrons you have, perfect Hamza. Yeah, the more perceptrons you have, the more overfitting you get. The green area is the error. Yes, it's there. Yes, exactly, it's there. So 2 red flags, as Hamza pointed out, you have generalization and optimization. So generalization, basically overfitting. The more perceptrons you use, the more you will be able to fit to the overfit to the training set, and the more, right, your generalization will be poor. And optimization, because now you have to learn, right, the weight for 16 perceptrons rather than learning the weights for just, right, 1 perceptron. Or in other words, right, how do I, minimize the error, right, when I have 16 perceptrons at the same time? When I have an XOR, for instance. What is the loss function? How do I minimize it? And so on. It becomes very complicated. Yeah? So these are 2 red flags. The more layers you have, the more perceptrons you use, the more likely you will overfit, and the harder it becomes to optimize. This is, folks, what neural network is. This is just an introduction for it. In reality, it looks like this. I have an input space which contains of D features plus the the 1 for the threshold or the bias. So that's the input. I stack it into, right, or I pass it through a network of neurons. So each one of these guys represent a neuron. So each one of the thetas represent a neuron. Okay? All right. And I have here few layers of neurons. So I have 1 layer, 2 layer, 3 layers. So this is a 3-layer neural network. Okay, so the input we refer to as X, it has D dimensions as we are accustomed to. And then I have the hidden layers goes from 1 till L, where L is the output layer. So this is the output layer. This is hidden layer 2, this is hidden layer 1, and this is the output layer. Okay, some terminology. Now, each one of these edges that you see, right? So this is a fully connected neural network, meaning that the input is going into every neuron. Okay, each one of these edges is associated with a weight. So it represents a perceptron, if you wish. So the blue lines are just weights, the red lines are just weights, and the green lines are just weights. Okay? So each one is a weight, Wij of L. Let's see what does this mean. I is the input, J is the neuron that it's feeding into, or the output, and L is the layer. So I have this one is W0 because this is input 0, 1 because this is neuron 1 of layer 1. right? So this is, because this is layer 1, W0, 1 of 1. The next one, what is this guy is? W1, it's X1 of 1, neuron 1 of layer 1. This one, for instance, the red one here, it's W2, okay? So coming from the second input to neuron 2, so 2 of layer 1. This, let's say, green one is WD of 3, neuron 3 of layer 1, okay? So these are, every edge of here is associated with the weight Wij of L. Let's see the second layer. This is W0, 1 of layer 2. This is W, the red one here is W1 of 2, because I'm going into neuron 2 of layer 2. This is W3 of 2 of layer 2, and so on. Okay? So L is the layer index, J is the input index, I is the input index, sorry, and J is the output index. All right? Now, I have the input of a layer is the output of the previous layer. So let's see what this means. I have weights here. These weights are multiplied by the input, the x's, summed, and that gives me a signal here. Right? So S, this would be S1 of layer 1. This is S2, signal 2 of layer 2, of layer 1. And this is S3 of layer 1. So S, J of L, yeah, where J is the index of the neuron. So S1 of L, S1 of 1, S2 of 1, S3 of 1. What is S1 of 1? It's basically weight times feature value. So weight times feature value. Yeah, blue lines times their feature values. Yeah, S2 of 1 is just the red weights times the feature values. And so
مش قصدك أول وحدة S2 because we have the one above it.
لا. So this one doesn't count as a neuron. This one.
But the first one counted as a neuron.
It's not counted as a neuron. This is the input.
Okay.
Yeah, these are the neurons. All the ones with the theta.
Okay, but it was counted as the first input, أول one.
Yeah. But it's not.
Okay, so كرمال تالت layer, the one we count it as an input كمان.
It's
the
second
one.
That's the edges here coming from the one are the threshold, right? Or the bias. The W0.
Yeah. Okay.
So this is neuron 1, neuron 2, neuron 3. This is not a neuron.
The W0 اللي احنا بنحطها okay.
Yeah, basically this is not, you see, it's not a neuron because there's no input coming into it. If you see, there's no input coming into it. Neurons are
because this is W0 احنا بنعمل مثل initialize شيء.
Yeah. Okay. So now I have S1 of 1 here, which is basically summation of the weight of this edge times 1 plus the weight of this edge times x1 plus the weight of this edge times x2, etc. That gives me the signal here. This the same thing for the red lines, the same thing for the green lines. So I have 3 signals passing through these 3 neurons. They get activated. What is theta? It's a nonlinearity, similar to logistic regression. So remember logistic regression, we pass the signal through some nonlinearity, the sigmoid function. Neural networks, you also pass the signal through some non-linearity. Okie dokie. So let's see what this gives me. So I pass the signal, which happens to be summation of the weight times the input from the previous layer through some nonlinearity theta. Okay, this is one example of a nonlinearity that is used in neural networks, tan H. Just one example. Yeah, what is the formula for tan H? It's e to the power of s minus e to the power of minus s over e to the power of s plus e to the power of minus s. Okay? So this is a signal. I know it. If I have the weights, if I have the input features, I know the signal. Raise it to the power of e minus e to the power of minus s, and then divide by the denominator. That gives you some activation. Yeah? This I call the input for the next layer. So x1 of 1, x1 of x2 of 1, x3 of 1. Yeah? So signal 1 of 1, pass it through the nonlinearity or the activation, and it becomes x1 of 1, the input to the next layer. Yeah, so x1 of 1, x2 of 1, x3 of 1. Okay, what are these? These are weights again, so I have to learn them. Multiplied by now the input, which happens to be x1 of 1, x2 of 1, x2, x3 of 1. That gives me a signal here. That's S1 of 2, of layer 2. And this is S2 of layer 2 because I have only 2 neurons here. Pass it through some nonlinearity. That gives me the x's here, so the activation. So x1 of 3, x1 of 2, sorry, x2 of 2, multiplied by the weights here. That gives me signal 1 of 3. Pass it through the nonlinearity here. That gives me x1 of 3. So xj of L is equal to theta sj of L, which is basically summation of the weight times the input from the previous day. Okay. So what do? I apply the original input. So I assume the original input here is layer 0. Yeah. So this is x0 of 0, x1 of 0, x2 of 0, and so on. Yeah. And then apply it. So I can assume that I have the initial weights or some weights. I can apply all of this. I can get all the activations and all the signals, assuming that I have some weights on these edges, yeah, which can be initially random, and then I update them as we will see how. Okay, questions so far? Good. So let's do back
sir?
Yes.
Could there be multiple learning on every layer? Not every layer, on some layers.
Multiple what?
Learning, like on the first layer, the algorithm learned, and the second layer it learns again on some different data or different.
So we'll see an algorithm that learns over all the layers. Yeah. So it looks at the error here at the output and learns the weights over all the layers at the same time. But you have different weights.
Oh.
For every edge here, you have a weight. Yeah, and you need to find this weight.
Yes. Okay. Thank you.
You're welcome. Okay, so this is where it gets tricky, guys, because we have to do some mathematics. So computing the weights. Now that my job is to compute the weights like any other learning algorithm. I have weights here. I have some input. I have weights. If I get the weights, I'm done. Yeah. All I have to do to predict the h of x, or the final prediction, is multiply the weight by the feature value, pass it through some nonlinearity, multiply by the next weight, blah blah blah, pass through some nonlinearity, multiply by the weights, and then I get some prediction here at the end. Yeah. So how do I get these weights? That's the question. So I have to find the loss function and minimize the loss function with respect to the weights. This is called back propagation. Yeah? That's the foundation of neural networks. So give me a second, 1 second. Yeah. Let's pause. What is S1 is H1? What does that mean, Salim? Can you explain? So signal 1 is not hypothesis 1, it's really right, the signal for the hypothesis 1. Yeah. So
signal 1 is the sum of the weights.
Yeah, sum of the weights
Right.
plus the feature values, exactly. Okay. All right. So now we want to learn these weights. So, okay. So basically, the final hypothesis is determined by all the weights Wij of L on every edge in the neural network. So to compute it, we're gonna use stochastic gradient descent. So the gradient descent version that looks at a single example. So let's say the error of one example is denoted by this E h of xn yn, which is some difference between the label, the actual label, and the predicted label, or the actual value and the predicted value. We'll call it E of W because, right, we want to find this with respect to, we want to find W that minimizes this error. So it's a parameter of W. Okay. So how do I implement stochastic gradient descent? I need the gradient. Yeah, I need to compute the gradient of this error function. So partial derivative of this, or the derivative of this function with respect to the W. That's what gives me the gradient. So basically I need to compute the error function or the derivative, right? Partial derivative of the error function with respect to every Wij of L for all Ij L. So I have, for every weight, I compute the derivative and then update the weight based on this derivative. Yeah, so the old weight minus eta times the derivative of the error function with respect to this weight. Before we did it in a vector form, but I can do it individually. For every weight, it's the same. I apply stochastic gradient descent on this weight alone. All right. So computing this.
Sir, بس شغلة. For the exam, هو الexam on Thursday and the deadline assignment on Thursday كمان.
مظبوط.
So can we make just the deadline تبع الassignment بس لFriday بس نهار من بعدها?
We can do that, yeah, sure, no problem.
Okay, thank you.
You're welcome. Okay, so we'll extend the deadline for the assignment if you guys want. Yeah, maybe a little bit more as well. Maybe till Sunday or something. Yeah, would that work?
Yes, thank you so much.
Perfect.
That would be really good.
Okay, very good, very good. Okay, so back to this thing, right? Ideally, we want to compute the weights here on these edges. So I'm going to do the following, right? I have an error here. I'm going to differentiate, right? So get the error, differentiate the error with respect to every weight that I have, and that gives me the gradient. And use stochastic gradient descent to update the weight by setting it to the old weight minus eta times the derivative of the error with respect to the weight. Okay. So I'm going to use chain rule. So I have the error here. Yeah, let's assume I have an error somewhere, which is at the final layer. Yeah, I have the final layer, gives me a prediction, and then I have the actual label, so I can compute the error. I'm gonna compute derivative, and I want to update this weight, Wij of L. So I need to find the gradient of the error with respect to this weight. That's what allows me to update the weight. So I'm going to do this. I'm going to say the derivative of the error function with respect to the weight is equal to the derivative of the error with respect to the signal times the derivative of the signal with respect to the weight. So chain rule. Yeah, this is nothing fancy. Okay. So what is the derivative of the error with respect to the signal? This we don't know. So we're gonna call it something. And then we have the derivative of the signal with respect to the weight. Anybody can tell me this? If you can, then you're following. If you can, then you're not following. I'll be frustrated. It's X. Perfect. Yes, Hamza, it is X. This is excellent, right? So why is the derivative of S with respect to W is X? Because remember, right? S is equal to what?
Let's say W's times X's.
Exactly. It's summation of W's times X's, and I'm doing partial derivative with respect to particular W. So I get only X. So the derivative, this derivative is nothing but X, right? And this
We get the X corresponding to the W we derived منه.
yes,
right? And correspondence.
مظبوط.
Okay.
And then I get, right, this thing, D of error by the signal, we call it some delta J of X. Okay?
But how will that help us?
We'll see how this will help us, yeah? So we'll see how to do this. So I think I'll stop here, right? This is way too much for you guys. I want you to do the following before the next lecture on Tuesday, to read this carefully, yeah? So that you can understand how backpropagation works. It's very important if you want to train neural networks and if you want to do deep learning. So you really have to understand this. And so please read all the slides on neural network until we meet on Tuesday. And then I'll repeat this. But I don't want to come on Tuesday and then you guys have forgotten everything and we lose the pace of how we do things. Yeah, so I'll repeat backpropagation on Tuesday, but please read and get familiar with the setting of the neural network. So understand it really well, and so we can build on it and see how to get the weights. Okay? Good. Any other things you want to tell me? How are you coping? Are you managing? Are you depressed? What's the situation?
Yes,
You're coping or depressed?
we are depressed. And like, it's a mix.
Yeah. Okay. So I know I am depressed too. It's really difficult for me as well, but we're trying our best and we'll get through this together. So let's see. The important thing is that this is cool, right? You really should learn machine learning before you graduate, right? As a computer scientist, it's going to be very helpful for you. It's really the most booming area right now in computer science. So Hamza prefers, for instance, online sessions. So maybe we'll stick to that in the future as well.
Same, sir. We all prefer, I think, online sessions, but the professors are like overwhelming us with projects when they know that we're home sitting doing nothing. They just keep bumping.
I'm keeping the same pace, so I don't know. Am I overwhelming you?
No, not you. I'm talking about other professors. You and we are already like for weekly assignments. بس الباقي لا.
Well, the simplest tasks become like 100 times harder right now.
Well, how is that? So what do you mean?
And if we had been given the same load without this circumstances that we're in, it would have been manageable. But like the same exact load is so much harder right now.
Yeah. Because of the other courses, right? You mean?
The other courses, because of the mental situation, like everything all at once.
Are you staying at home? You're not, guys, are not going out,
Yeah,
right?
I am. I'm 24/7.
Yes,
Good, good. So stay at home, right? Try to, we'll get
we
through.
sometimes go out to the balcony.
Okay. That's good. That's good. I don't even go to
Feeling
the
wild.
home. Well, we'll see how things. It's tough times, right? We have the last semester, we had the Thawra, and now we have this. So we don't know where we're heading.
This year was just amazing.
Tough for you guys, yeah.
Yeah.
Well, we'll see. We'll see what happens. I hope things get better soon for you guys. Yeah, I mean, I've had, I've had a great undergraduate and graduate studies, so I feel sorry for you. I mean, you're really going through a lot, so I feel sympathy for you. You shouldn't have to go through this, honestly. Yeah, it's the best time, being in.
Are you saying the exam won't be hard?
It's not hard. In my opinion, it's not hard. Really, it's not hard. It's just multiple choice. I don't know what else to do. I mean, if it's multiple choice, I mean, how easier can it get? And you just either know the material and know the concepts, or you don't. Yeah. So I'm not. It's really not tricky at all. It just really tries to find if you know something about what we've been talking about the whole semester. Yeah. So it's not difficult.
Some people are asking if it's going to be open book or if it was originally supposed to be open book.
It's not, originally it wasn't supposed to be open book. I'm not in the instructions. It's going to say it's a closed book, but good luck with me trying to control that. So.
Okay, so it's supposedly not open book, even now.
Yeah, it's not. It's supposedly not open book, but I mean, you have an hour. So it's going to be an hour. Yeah. So also, don't waste your time too much looking at things and stuff like this. Maybe you can do it for a question or two, but if you keep looking at things, you run out of time.
Yeah, akid. No, yeah, I was just seeing what's how it's supposed to be.
Yeah, it's supposed to be a closed book.
Okay.
Yeah. How are you coping with the assignments? Are you starting to feel like you're comfortable with machine learning? You're learning. You're more comfortable classifying.
Yeah, working with libraries is.
What's that?
I find the recitation sessions that Shadi is doing are very good.
Yeah, great. So you're more happy with the libraries rather than the building things from scratch.
Yes.
Especially the solving sessions with the Shadi. Other courses are not doing that. It's really helping.
Good.
Yeah.
It's a good evaluation, ICE evaluation then, yeah?
Yeah, it's definitely been the biggest help, هدول recitations مع Shadi. Show us how to solve the assignment.
That's great.
And even easier من أول السمستر كنا ضايعين شوي.
معلش. So I'm glad this is working well. So okay. Somebody has a question about. So you can leave now, right? I'm done. I'll repeat the gradient descent again next time, but please read the slides before Tuesday. Yeah. And then I will answer as a private question that I have.
Thank you.
Yeah, we'll see you guys.
Okay, goodbye.
Bye.
Sir?
Yes.
I sent you an email about a week ago asking, because me and my group, we were still finalizing our project idea before the outbreak happened. And I sent you an email, but you never responded.
What was the email about?
It was about the proposal. Now we're thinking about making an AI that plays Tetris.
Okay. So I don't know the game, right? So yeah. So
I'm pretty sure you do know it. If you saw it, you would definitely recognize it. It's the one where you have the blocks that fall and you have to arrange them in a way that the screen. You don't know it?
Yeah. So I'm not really sure. I don't play any games, honestly.
Okay, fair enough. This one's a classic, though. That's why I thought you might know it.
No, I probably don't, right? So I really don't.
Okay.
So it's fine. You can do that as part of AI, yeah. But this probably involves reinforcement learning. We're not gonna cover it in class. It's very close to what we cover. So really, I mean, really, it's nothing more than some minimization of error and so on. So you can definitely do that, and you will find probably some starter code and some data you can use. So it's fine, yeah. But like, I mean, what
Okay.
was the original idea? Did you have an original idea, or you didn't submit any original idea?
We still didn't submit anything because I was waiting for your response to my email, but I figured now would be the best time to ask.
Yeah. Okay. If you're excited about it, sure, right? But it might be slightly off from what we're covering. That's what I'm scared of. Yeah. So you might be on your own a little bit, trying to figure out how to deal with how we achieve the project. Yeah.
Okay, that's fair enough. هلا نحن we found someone online doing something similar. We want to find a way to do it differently. Basically, that's our goal.
To do it what?
Differently, like not exactly the same way he did it.
Okay. So at least you can try with this. Start with what he's doing, and then see how you improve on it. Yeah.
Okay, perfect. So you approve basically.
Yeah.
That's
Yeah.
my question.
Yeah.
Okay, amazing.
Good.
Thank you, sir. Have a good day.
Good, guys. You too. Bye. Okay. So where was the question? The private question. Yeah. Why did we do partial derivatives? No, we did partial derivatives because we have to minimize the error, right? The error that is here with respect to every weight that I have. So every weight that I have is a partial derivative, yeah, because you have an error function which depends on all the weights. What I'm doing, right, I want to minimize it with respect to this particular weight. So this is a partial derivative. We'll repeat this again in the next lecture when we talk on Tuesday. Yeah, that good enough? Yes, to minimize EN, exactly. Okay? Yeah, you're welcome. Bye-bye.
Goodbye.